Okay, we are now recording. Let's get the slideshow set up for the current slide. Now I'm looking at this. I used a different book last time. I had a mark on it. Did we already do? No, we didn't do this one, I don't think. No, I think this is the right place. Okay. All right. A couple of announcements, not too major, but a little bit. I believe I told you last time that they had changed my schedule ever so slightly. Well, my schedule stayed the same, but they decided to pay me for one overload course. So if I'm teaching like 4 overload courses, they're going to pay me for one of them, or combine them and make them one. So anyway, that meant that I have to stay longer hours because that's beyond the normal workday. So I had to adjust my syllabus and my locator card. And I think in class on Monday, I hadn't had a chance to get that done yet. I did get it done yesterday, so what your syllabus on Blackboard now has the correct office hours, and so does the locator card. Basically, I was leaving at 3:30 on Tuesday and Thursday, now I'm leaving at 5:15. That probably does a little bit extra hours, but it just depends on whether they're paying for a physics course or a calculus course or a differential equation course. They're all different, hopefully one of the 4-hour courses. Anyway, those have been corrected. So I think everything's up to date on your Blackboard. Hope so anyway. Well, with maybe some exceptions. No, I was thinking somebody had turned in a paper so far, but that was in the physics last time. Either of these 2 classes. I don't have all the grades out there yet, so I'm getting those done as soon as I can. All right, and here's Richard. Okay. I was just saying that I have updated both the syllabus and locator card on Blackboard just because they decided they would pay me for one overload, but that meant I have to work extra hours, so I adjusted my office hours. Tuesday, Thursday now goes till 5:15 rather than ending at 3:30. Monday, Wednesday stays the same here till 9:15. Actually, I did move that up a half hour, 15 minutes to 9:15 because I never get away before that anyway. All right. We were talking last. Any questions on anything we've done up till now? Okay. We're talking last time about density. And we had talked about density, total mass is linear, and okay, we're starting with looking at long rods or tubes or strings or things like this that have one dimension basically to them, okay? Not plates of steel or volumes of something, but rods that have just one dimension. And then we deal with what we call a linear mass density, which is what the row represents here. Most of the time in physics, when you think density is mass per unit volume, this is a linear mass density, so it's mass per unit length. So rho times delta x would then give you mass, because x is a length, and this is mass per unit length, so that would make sense. Okay. Now, and I think did we say anything on density, or is that where we're starting? See, I was using a different book last time, and I made a mark in it, but I didn't make the mark here.
The only thing we had was total mass.
Okay. Okay. So that was the first thing. Now, if that rod was uniform density, you just multiply the density times the length, and you got the mass. That's pretty simple. However, life is not always so simple. Here, your density of this rod is a function of x. Here, it starts at a fairly low density here, gradually increases in density until it gets right around here and is very dense right there, and then falls off fairly sharply to density here. So here, the rod is much denser here than it is here or there. Okay? So this now shows density as a function of displacement from the end of the rod. Starting at x0 equals a, to x of n equals b. cut this rod into, they look like here they're equal length, it doesn't matter, just any kind of partition, preferably equal. So you've got x0 is A, then x1 is the first cut, x2, x3, and somewhere out there you get the ith minus first cut, and then x of I, the ith cut, and then you keep on going until you get your nth cut, which isn't really a cut, that was the end of the rod, and that's your B. Okay? So you cut this rod into increments here, small pieces. Now, if this is your first piece right here, its density is not quite constant, but pretty close to it. Okay? The next one is pretty close, next one pretty close, the next one pretty close. Somewhere up here you're going to get one that's really very close to being, really close to being constant. Then these are not particularly close, but it doesn't matter. You can take the average density there. So let's just take, and it doesn't even have to be exactly average, let's just take the density at some point Ci that's in between xi minus 1 and xi. It could actually be one of the endpoints, usually it's a midpoint or some point in between, and use that density. Okay? So we'll choose that right there and use that density right there and say that's the density of that whole weight. It may not be, but it's going to be pretty close. Okay? So then what you do, your total mass, rather than being length times density, which would be for a constant rho, your constant density, now you have rho as a function of c sub I, which that is for every increment here, it's some intermediate value that's in that increment, and then multiply that by your length, and that gives you a very good estimate. Much better than taking the length times, say, the average density of the whole thing. That might be good, but how do you get that? If you do the density of each piece, that makes a lot more sense. Or, it's sort of easier to do conceptually. So there's the total mass of the rod is equal to the area under the graph, okay, of the mass density. So if you go from here, this area here, which they didn't color in, that would be the total mass of the rod from here to there. Letting that represent density as some mass per unit length times these various unit length. Okay. Now, of course, you go from xi minus xi minus 1, which would be a delta x of I, to smaller and smaller increments, meaning a lot more of them. And then rather than summing up a whole bunch of little numbers, you ultimately get to an integral over the range from A to B. And that's where we're going to head. Basically a Riemann sum. So here is then carrying that out rather than summation of all those little pieces, making an integral from the left end to the right end, A to B, of your rho of x. Now that rho is a function of your displacement here along that. You have to have that formula times your dx. This is mass per unit length times length. That gives you total mass. So very similar to what we did before, only now we're dealing with densities and lengths, whereas before we were dealing with areas and volumes. But pretty similar. Before, we had to calculate those areas, which that was your hard part. Here, they usually give you the density function, so that makes it a little bit easier. Now, I don't believe they have a slide for example 4. Or do they? No, they don't. Okay, that's the next thing. So we'll go with this. Let's do example 4. Find the total mass M, so that's what we're looking for. Let me get my pen color adjusted. Okay. The system seems to be taking 2 clicks of everything to get something done today. Okay, so we're looking for the total mass, like we're talking about here, of a 2-meter rod. Okay. of linear density rho of x is equal to 1 plus x times 2 minus x and that would be in kilogram. I'm sorry, where did the D come from? I don't know. I'm used to writing delta, I guess. Okay, kilogram per meter. Okay, that's the unit for it. The rod is 2 meters long. The density is given in kilograms per meter, where x is the distance from one end of the rod. Okay. Now, let's do a little quick timeout here, and let's just see if we can picture what's going on. From that last figure we had, the density at when x is equal to 0 would obviously be 1 kilogram per meter, right? So 0 there is over there. Now, from there on, the density is slowly going to increase because your x is increasing, going from 0 to 2. Obviously, that's going to be the end. It's going, so the x is increasing. The 2 minus x is actually decreasing, but it starts, past. So another way to look at that is actually do the multiplication, which is what I was going to suggest. 1 plus 2x minus x squared. Okay? Now, what's that shape? That's a parabola. Okay? And it's going to be 1 when x is equal to 0. And when you put x equal 2, then that quantity in parentheses up there is going to be 0. So it's 1 again. So in between there is a parabolic shape. Okay? That probably doesn't go up that steep, but it is a parabolic shape. So, how would you find the total mass of that rod? The integral, so that m is equal to the, what's that integral? 0 to 2, from one end to the other. 0 is the first end to the other end of 2. And I would use this form here, I think. 1 plus 2x minus x squared, then dx. I've got a sneeze, excuse me. I want to make sure y'all hadn't fallen asleep while I was talking. Okay. Never mind. Poor folks at home, they probably didn't feel that coming. But what do we do here? Integrate. What does that give you? Antiderivative. Say again?
0.
No, you're not taking derivative, you're antiderivative.
Oh, that's right.
X plus x squared minus x cubed over 3. Evaluated from 0 to 2. Sneeze loosen things up here. Plug in the 2, and what do you get? 2 plus 4 minus 8/3. I'll do the 0 part. Okay, got it. That's someone coming. Yes. Okay. And this is Khalil? Yeah. Okay. I didn't get the thing done yet. Hopefully tomorrow. Okay. I'm sorry it was taking a while, but I had a bunch of paperwork I had to take care of yesterday that took way longer than it should have. Okay, so what does this come out being?
6/3 plus 12/3 is 18/3 minus 8/3 is 10/3.
Oh, okay, so you're doing 6/3, that's 2, plus 12/3, which is 4, minus 8/3, and that would be, what do you say, 10/3?
Yes.
Yeah, 10/3, or or 3 1/3. And that would be in units of kilograms. 3 1/3 kilogram would be the mass of that rod. Does that make sense? Okay.
Just to focus on the 12, it should be a third. And
Oh, third.
3 in the denominator. You're good.
Yeah, I was thinking 4 and wrote a 3. I mean, didn't write 3, wrote 4. Oops. Okay. Yeah, got it. Okay, now, that's dealing with linear mass density, and if they give you the density function, it's usually pretty easy to calculate. Okay. Now, in some situations, we don't talk about a linear mass density, but we kind of, and this is not probably a proper term, talk about an area mass density. For instance, population. If you think about a lot of cities, now this is changing somewhat now, but they have the densest population near the center, and then as you get further out, maybe the population falls off, especially if you have an industrial area around there. But then if you get to suburbia out here, the population density may increase again. So you may have what they call a radial mass density. This is Chris, right? Okay. Slowly, we're all getting here. We're just missing Stuart and Anthony. Okay. All right. So that's what we're going to go to next. It says, in general, density is a function of two independent variables like x and y, depends not just on the distance from the origin, but also on the coordinates x, y. Total mass or population is then computed using double integration, but we're going to get into that in Cal 3, not here. But if we deal with areas this way and do it in radial, okay, in other words, basically are going to use polar coordinates rather than xy coordinates, and it doesn't matter the theta, just the radius, then you're still in single variable calculus. So that's what we're going to do now, do a radial density function, which is still per meter, because it's how far you are from the center. Okay? And here's the figure that they're going to use to come up with what they're talking about here. Now this is making the assumption that everything expands similarly in all directions. You know that's not always the case. Say in the Birmingham area where you have Red Mountain down here, you know, you're not going to have the same population density in all directions. But someplace more like, say, Atlanta, which doesn't have, say, a mountain cutting through it or something like that, it kind of could fit a radial model. Okay? So if this is your city center or wherever you're talking about, and you're dividing the circle and the radius into n thin rings, each of these is now, here we're dealing with a radius. You're going so far out from the center, so that's going to be some value r. You could call it x or y, but that usually puts you in that frame of reference. Call it r, that could be r in this direction, that direction, any direction there. So you split this in your total radius. The city boundary is a capital R out here, and you're going to split that into n thin rings. Okay? And this is a lot like we did before, but now we're assuming you've got uniformity of spatial, that you don't depend on theta. You don't change any of your population or whatever you're talking about as you go different angles, only as you go different distances. Now, if this were talking about sound energy from a source here, sound goes pretty much uniformly out as long as you don't change medium. Light intensity, lots of things follow patterns that are like this. okay, as long as you don't have any dependence on what the median is there. So we're going to split this total radius here, 0 to R, capital R here, the outer limit of your population, your city, whatever it is. Then you're going to split this into n thin rings, 1, 2, 3, I minus 1, I, up to this last one would be R sub n, little r sub n, which would be capital R. So you divide that into those, and then what you have to have is a density formula, but that is per unit area now. So then you have to deal with, even though you don't have a theta dependence, you need to deal with the area of this ring. Because obviously this ring has a smaller area than that one, and that's less than this one. It's very uniform thicknesses here, delta R's. The area of this ring that's going to be centered at R sub I, or not centered, but limited by R sub I, that's going to be approximately, now not exactly equal to, the circumference of this ring, that's the length times the thickness of the ring. Now obviously that's not quite true. You can't take this and stretch it out here. This length here is less than that length there, so you have to do a little fudging, but that's why it's approximate. Approximately equal to the circumference of the ring, 2 pi r I times the thickness of the ring, delta r. Okay? So that's going to be your area. So they're going to need your density function as a function of area, not as a function of length. Okay? Even though you only have one variable length, you have to deal with the whole area. Okay? So, the population P within, say, that radius R, capital R, your outermost thing, would then be the total population. Now this is the R is equal to, it's population P. So I would have the P right here. P is equal to, okay, the 2 pi is from your circumference, 2 pi R, rho of R, where this is a area density, okay, and the R goes from 0 to capital R. Oh, the dr was your thickness. So 2 pi R is the length, rho is the density, and delta R is, or dr is the thickness. So 2 pi R dr is the area, and this is population per unit area. Okay, so it's sort of separated, so, but that's what that formula looks like. Now, they did remind some type things before that to lead up to that, but I think you see how that goes. Let's just go back here. What you do then is have more and more larger and larger n, smaller and smaller delta R, so that leads you to that the limit of that is dr, and then your area is getting closer and closer, because the thinner this is, the closer that is to the area of a rectangle of length 2 pi r, thickness dr, okay, delta r, and then you integrate that from 0 to r. Okay. All right. It's a different problem, so let's do example 5. Computing total population. The population of a certain city has radial density function of rho of R, okay? Even though it's a radial density function, it is per unit area, okay? And this would be 15 times 1 plus R squared to the minus 1/2, okay? Where R is the distance from the city center in kilometers, and rho has units of thousands per square kilometer, okay? So how many people live in the ring between 10 and 30 kilometers from the city center? So we're now interested in just 10 to 30 kilometers. We're not interested in the whole city population, just in that ring between 10 and 30 kilometers. Okay. Now that's going to change your formula just a little bit because you're not interested in 0 to R anymore. You're just interested in 10 to 30. Okay. Let's pause a moment before we go there. What would be, and remember the population was in tens of thousands? No. The density was in thousands per square kilometer. So at city center, that density was, if that's 0, this is over 1 square root. So that'd be 15,000 per square kilometer. Okay? And as you go out some, let's say to radius 1, that would be 1 plus 1 squared, that would be 2. Square root of 2, 1.4, that's in the denominator, so 15 divided by 1.414, so it'll be a little bit less. And you keep going out, and now this is 1, you can never reach an end, okay? You'd have to have some limit out there to say that's all, folks, because technically that would have a tail that approaches 0 but never gets there, okay? But yeah, that's what the density is looking like, maximum in the center and falling off as you go out. Okay? So, what would be your formula here? Your function here? The population would be, and don't forget the 2 pi, the integral from 10 to 30 kilometers, and this was in kilometers, the delta R was in kilometers per from the city center, I think. R is the distance from city in kilometers, right? Okay. Make sure the units are right. Now, notice that 15 just a constant. Let's pull it on the outside too. Why mess it up in the inside? So this will make what's out here at 30, right? 2 times 15 is 30. And then you would have basically 1 plus R squared to the minus 1/2 dr. Right? Okay. That's kind of a yuck, isn't it? Can't think of a substitution that's going to help us here. Well, I can, but not a regular one. What will help us? Especially if we write this as 1 over square root of 1 plus R squared. What does that kind of... No, that's not even right. Okay. I think there is a substitution that's going to have to work. Oh, wait. No wonder I messed it up. I left out part of the formula. Okay, let's scratch this. Remember, it's 2 pi R dr. You do have an R in there. Okay. Now this works much better. Okay. 2 pi R rho dr. I forgot this little R here. Okay. Now it works quite nicely. What would you use to solve that?
You substitute the 1 plus R squared.
That's what I would do. And what do you want that to be? Our favorite U? Okay. U equal 1 plus R squared. Again, substitute the innermost part of the most complicated thing here. Things in the denominator to have 1/2 power. Yeah, that's the most complicated part. Then what? du is equal to 2R dr, writing in differential form. Okay. Now we have a RDR up here. We don't have a 2, so we may want to divide this by 2. You're going to find out we're going to be flipping and flopping 2's all over the places here, so just keep up with them. All right. So if you pull this 2 then on the outside, that gets this back down to a 15. Okay. So keep up with them. Okay. Don't lose them. Okay. So this now new integral is going to be 15 pi. Okay. I'm going to put my integral sign. What do you want to do with that 10 and 15? 10 and 30?
Did you also divide that by 2?
No, you don't. Those are your limits here. So those are the limits of r here, so you change that to u here.
Okay.
So plug in for r a 10, and that would be 101. Okay? And the other would be 901. Boy, these are not looking pretty, are they? Okay? What then becomes what you have? What else do you have now? U to the negative 1/2 du. Okay, even though the limits are kind of messy, this is not too bad. 15 pi, and what you have here, I'll do a bracket here now. Antiderivative of that would be
Negative 1/2 u.
okay. Now remember you're integrating antiderivative, not taking a derivative. It's going to be a u. Say again. U to the 1/2 over 1/2, which is times 2. Like I said, you got 2's flying all over the place here. Keep up with where they are. Divided by 1/2, which is the same as times 2. Got it? Okay. Evaluate that from 101 to 901. Okay. Ugh. Okay. Again, I would take this out and make that a 30 again. Okay. So you got 30 pi. And now you've got some calculations to do. Okay. Pull out the old calculator, do the square root of 901, and subtract from that the square root of 101. Anyone have a calculator with them?
Or do we plug it in? Square root.
Yeah.
19.96.
Second,
19.96.
is that with the 30 pi or is that just that?
Oh, well. Well, that's
1,880. Is that what you said? 81, yeah. Whoops. And that would be 1,000. This is a pretty big city, folks. That's got 1.9, almost 1.9 million people in that 10 to 20 kilometer radius, meaning the densest part is still inside there, and you still got some on the outside as well. So, pretty big number, okay? So in other words, population of approximately 1.9 million people in that band between 10 and 30 kilometers. Okay. Now, just as if that was indeed 900 and 100, it's not going to be much different, all right? That would be 9 minus 1 is 8. 2. Yeah. It's 90 minus, 30 minus 10. 30 minus 10 is 20. 20 times 30 would be 600. Do 600 pi and see what you get. 84, okay. So you see it doesn't make a lot of different. You still go around another 1.9, right? Okay. So you could have saved a little effort by just estimating. I wasn't sure how close that would get. It got you close enough, especially for two-digit estimate. Okay, so there's another example of application of integration, getting population, if you have a population, radial population formula, density formula. Those are not particularly easy to come by, okay? So you'd have to get that from somewhere. All right, next application here is going to be fluid flow, or flow rate, but generally you got fluids. But remember, when I say fluid, what does that mean? When I say fluid, what do you think? Water. But you see, fluid doesn't have to be a liquid, it could be a gas. Same thing applies to the air coming through the ductwork as for water going through a pipe. Okay? Fluid flow is fluid flow. Now, densities and other things are very different, but the principle is still the same. Okay. When fluid flows through a tube, the flow rate Q, so that's what we're looking at. I can't write on here, so let's just talk about it for a minute. The flow rate Q is the volume per unit time. Okay? Typically, ductwork, we talk about cubic feet per minute, volume per time. Water through a hose, you would probably talk about maybe something like liters per second, liters per minute, or something like that. So it's some sort of volume measurement per unit time. Okay. The flow rate depends on the velocity of the fluid, which I do not like the way they do this. Okay. They put V centimeters. Okay. That sort of grates on me a little bit, because I think of V as being a velocity, but it's not measured in centimeters, it'd be centimeters per second. So, or minute, or something like that. I don't like the way they label that. I think there's a reason they put it that way, though. If all the particles in the fluid traveled at the same velocity V, say in units of cubic meters per minute, they're really messing up the units pretty badly here. That's not a velocity, cubic units per minute. That would be the flow rate. That would be cubic units per minute flow rate, but at some same velocity, and the total flow rate was cubic feet units per minute. So they write it next to it as if that's the same. And the tube has a radius of R, then the flow rate Q, and let's see, I don't think they're going to do it. Okay. I'll have to shrink this. Okay. There, I got this wrong. Okay. So the flow rate Q, and that is in volume per time. I'm going to leave it like that so you can put in whatever units you want. Okay? Now, if all the particles were traveling at the same velocity, okay, and you had some flow rate in, they're saying cubic meters per minute, okay, then the tube has a radius R, then your flow rate Q would be the cross-sectional area and they're calling that, they should call it A. I don't see that they give it a name. But cross-sectional area times the flow rate, times, okay, that's an area, 10 times V. V is in meters per second. So if this is in square meters, times meters per second, or meters per minute, or whatever you're dealing with here, then that would give you volume per time. Area times meters per minute, or meters per whatever unit you're dealing with for speed, then that will give you your volume per time. So now, it's a little bit awkward here. Usually in physics, capital V means volume, little v means velocity. Okay? So,
Is that a lowercase nu?
what's that?
Nu? New letter nu?
Oh, is that's not a nu, that was supposed to be a little v. Okay, velocity. Okay. This is also a v here. Why they have centimeters, I don't know. But this is if all the particles are moving at the same velocity, then the cross-sectional area, which would be the area of that circle, if this is a circular pipe, times your velocity, that would be in, if this was in meters squared, and that was in meters per minute, then you have cubic meters per minute. Okay? So you would have the cross-sectional area would be pi r squared, where r is the radius of that circle. Okay? Pi r squared times v. That gives you your flow rate in cubic feet per minute. This is cubic meters per minute. Square meters, meters per minute, cubic feet per minute. Cubic meter per minute. Say it right. That's if all the particles are moving at the same speed. Likely to happen? No. All pipes have friction on the edges. The center may move, but then basically you have kind of a parabolic flow, paraboloid type flow profile, you might say. So this isn't very much realistic. This would be if you took the flow coming out of there as fairly uniform, and then you imagine the circle there that doesn't really have any friction to it, that would be the flow through that. And that's okay to do that kind of imagination here, but it's not really close to reality. That would be if you had constant flow. In reality, fluid particles do not travel at the same velocity because of friction. However, for a slowly moving fluid, the flow is laminar, by which we mean that the velocity, v as a function of r, depends only on the distance r from the center of the tube. Again, that's going to give you the parabolic type flow, but that's laminar flow. What's the other type of flow if it's not laminar? Turbulent. Turbulent flow means it's going so fast and there's so much drag here you get little eddies in there. Ugh. Miserable to model that. Laminar flow, a lot easier to model. So we're going to stick with laminar flow. Okay. So rather than this being the case, we're going to see flow that looks more like this. Okay? This is laminar flow where you do have friction along the wall. And because you have friction, you assume that actually the flow here at the boundary is zero. The flow in the center is your max, and then as you get closer to this, you follow sort of a parabolic kind of profile here. Now, I can't for the life of me figure out why they drew this way. The graphics person, if I were doing this, I would have flipped this bullet-looking thing this way and had the arrows like that. This makes it look like, I don't know what it makes it look like, but that just doesn't seem like reality to me. It seems like it'd be better to flip that over. It gives you the same thing, but it just is a weird-looking way to represent it. Okay? Velocity of fluid increases toward the center of the tube, and it's assumed to be zero at the edge, the way they've done it here, because you have friction there. Okay. Now, that leads you to, with that same type of thing in mind, remember that your your cross-sectional area is pi r squared. No, sorry about that. That was for the, if it was constant flow. So what you do here, you really set it up much like you did before. Yeah, here's the picture of it. It was passed over there, so I wasn't seeing it in my frame of vision here. Here it is. And again, they got the bullet pointing that way when it's really going this way, but I guess it's fine. And the laminar flow, the fluid particles passing through a thin ring, they're talking about this ring here, not a ring this way, but a ring this way. A distance Ri from the center, all travel at nearly the same velocity. Okay? Right at the center, they're all at the same velocity, and that next ring, as long as the ring is thin enough, it's close to the same velocity as you're going up. So this is the ith ring out there. Okay? So then the fluid particle passing through that would be the velocity as a function of that distance from the center. Okay? 0 at the center, capital R out here. Okay? So the ring of width delta R, this is just like what we did before in population. The ring of delta R, the thickness of delta R up here, and then you approximate that as if you strung that out and made a length of 2 pi r times delta R. That would be the area of this times the velocity going through that as a function of that R, that value R, and that would give you your the total flow rate. Okay. So this would be in meters per second times meters squared, meters per minute times meters squared. So that would be cubic meters per minute. Okay. Cubic feet per minute if you're using U.S. customary. Okay. And if you see the formula, can you tell any difference of that and the population problem? Basically exactly the same. For the same reason. 2 pi r is your area of that ring. dr is the thickness of the ring. That gives you the 2 pi r is the length of the ring. dr is the thickness of the ring. So 2 pi r dr would be the area of the ring. But now it's a velocity here, not the only difference here is the velocity profile as a function of r as opposed to a density function, radial density function. The rest of it looks just the same. Okay. Now, don't know if you're interested in the physics area of this, but there's a French, and they say a physician here. I think they mean physicist. I don't know that Poiseuille was a physician. No, he was. He was a physician because he was talking about laminar flow through veins and arteries. He was a physician, okay? And he came up with this. Didn't know the physicians. I don't know. They don't know this kind of. No, I'm just kidding. Came up with this flow rate through blood vessels. Poiseuille's law highlights the danger of cholesterol buildup because as your effective radius gets smaller, then you don't get as much blood flow. Now, as long as enough can get through there, you're fine. But then when it gets so small and you don't get enough, then organs don't operate well, as in heart. That's what causes heart attacks, when you get cholesterol buildup in the walls of your, especially the arteries feeding the heart. And that's what they do when they are looking at EKG. Well, is that what it's called? The thing that models, and so they look at the flow rates and they say, you're just not getting it. Now, nowadays they try to go in there with a stent, basically a balloon, and sometimes a actual mesh around the balloon, put it in there, then blow up the balloon and forces the mesh out into that, opens it up, and the mesh is supposed to, that's called the stent, keep that out. The old days, angioplasty was just the balloon pushing into the walls of the artery, and then you got the blood flow. Then they started doing stents if they thought that was going to collapse again. Of course, the danger with all that is getting the thing wound up there without damaging anything. And then when you blow it up, that the walls of the artery aren't hardened. You've heard of hardening of the arteries. That comes with age. So that therefore, when you blow it up, you may actually rupture it. That happens in emergency heart surgery because you're going to bleed out. So the alternate to that, in fact, it was what was done first, is actually go in and put a good, healthy blood vessel they get from somewhere else in the body, so another incision, put that where, take out the part that's clogged and put in. That's open heart surgery, and that's a lot more intense than angioplasty. But that's why it was a physician. All right. So anyway, according to Poiseuille's law, the velocity of the blood flowing through a blood vessel of radius r, centimeters. Now, guess what? When you're talking about blood vessels, cubic meters per minute is not the best unit to use. Okay, you don't have cubic meters. Okay, a cubic meter would be, picture this. Yeah, it's a metric ton of blood. Okay, we don't want something that's out there. This is about a meter from the floor. This is about a little less than a meter this way. Come out a meter this way. That's about 3 blocks out here. That would be a cubic meter per minute. Now, let's not use that unit for blood flows. So let's get down to centimeters, and that's why the earlier illustration had centimeters up there. That's a lot better than talking about. In fact, I wouldn't be surprised if capillaries and stuff, they don't go to millimeters, but we'll stick with centimeters because they have here. So the velocity of the blood in a blood vessel of radius r centimeters is V of r. Now I've got to come down from this. V of r, this is Poiseuille. Ooh, that's ugly, isn't it? My V wound up looking more like an R than my R did. Okay. V of r, velocity as a function of radius, was, this is Poiseuille's rule, K, which is a constant, times r squared, that's the maximum radius of that blood vessel, minus little r squared, that's whatever, that's the variable r, and where r is the distance from the center of the vessel in centimeters, K is a constant. It says calculate Q, which is flow rate. That will be cubic centimeters per second, I'm guessing here, yeah. And that would be 2 pi, remember that's from the 2 pi r. You're integrating from 0 to capital R, center of the blood vessel to the outer radius in centimeters. And then your R, okay. Well, okay. They're putting the constant here, K, they're saying, let's assume that is 0.5 centimeter per centimeter second. Okay. The thing is, it has to have, this has to be in centimeters per second. This obviously is in a centimeter squared. So you've got to have this having a per centimeter here, because you got to go from square to centimeter. So per centimeter, but this has a per second, there's no per second here, so this has now per centimeter second. So that's why you have that unit there. Now, we're doing a math class, who cares about units? But in reality, you do care about units in physics, in medicine, and every place else. So that K does have a unit. We're going to use it as 0.5. So I ask why you even put it in there. Take it out, okay? Take it out of there and put it outside. When you multiply 0.5 times 2, you get 1. So actually, I don't know what just happened there. Okay, here. Okay. So I use the 0.5 to wipe out the 2. Okay. Now let's go back. Okay. So I've already taken care of that. We have the r from the 2 pi r. The k was 0.5 and the 2, they wiped each other out. Okay. And then you have r squared, that's a constant, minus r squared, that's the variable. That's from Poisson's rule. And then you have your dr. Okay. Now, they're not telling you what your radius is. Okay. We're just going to do this. Okay. So we're just keeping r alone. So what I would do here is rewrite this as r squared, or maybe r squared r probably would make a little more sense. Capital R squared times little r minus little r cubed dr. That's what you're integrating from 0 to r with a pi out front. Okay? That looks pretty ugly there. Antiderivative of capital R constant squared r. What would that be? Here's my pi. Little square r squared over 2. Very good. Minus for the r cubed part. Antiderivative of that. R fourth to over 4. Right? Okay. Evaluate that from 0 to capital R. I'll do the 0 part. Okay. That'll be pi times capital R to the 4th over 2 minus capital R to the 4th over 4, and make this 2/4 rather than 1/2, and that gives you pi times R 4th over 4. Okay? Or 1/4 pi 4th R4, and that would be in cubic centimeters per second. Again, this is assuming your velocity is in centimeters per second, which is what we assume. So, the flow rate depends on the radius of those things. Now, think of a good-sized vein here. It's not got a big radius, but you know it can get a pretty good flow rate. Think of a capillary, which is about the thickness of a hair. How small that radius is, you're not going to get a lot of flow through that. Okay, but you got a lot of capillaries feeding into the one vein, so yeah, the body works it out pretty well. But if you have blockage in one area, then you can have some pretty major problems. Okay. The Q is proportional to R to the 4th, and that's true for any value of K. Okay. So that's what Dr. Poisson found. Now, this next application, so we've had applications of mass using density, populations using population density, flow rates, Poisson flow. Didn't we do one before that? Oh, just shapes, you know, volumes, okay, depending on shapes. And now flow. Now another application of integration is average value, okay? All right, we haven't gotten to the slide yet, so let me start writing that. As a final example, we discussed the average value of a function. Recall that the average of n numbers is what? What if you have 5 tests? How do you get the average?
Add them all together.
T1 plus T2 plus T3 plus T4, T4 plus T5, and do what? Divide by 5. Okay? Now, how they express this let's not call them tests, but just call them numbers, A1, A2, and stuff. So the average value is A1 plus A2 plus A3 plus ... plus up to A sub n, whatever that number n is, and you divide it then by n. All right. Another way to express that is 1 over n times the summation from j equal 1 to n, capital N, of A sub j. Right? I mean, that's what you did there. You added all these up. That's the summation of adding all those. Multiply by 1 over n. You do this from 1 to capital N. Okay? The j there is just a counter, making sure you're adding all those up. Okay? Now that's if you had discrete numbers. Okay? But what if you had a function here? Oh, and they give some examples here. Do we need to do that? Average of 18, 25, 22, and 31. Just add them together, divide by 4. And it gave you 24. They say, I like to do this. Let's see if 24 makes sense. 18 is 6 below it, so that's a minus 6. 25 is 1 below that, makes it a minus 5. 22 is 2 below, that makes it a minus 3. 31 is 7 above. I don't think they did the math too well, did they? No, I'm sorry. 25 and 31, that's 1 and 7 above, so it's 8 above, and it's 6 and 2 below. Yeah, 8 below. So yeah, 24 is right. Okay, I just got the numbers wrong. Now, what if you had something like this? Not discrete values, but continuous values. So how are we going to get the average values for that? Well, you could pick a few and just say, I hope these represent the ones that we got. The average value of f of x at these points would be f of 0, f of 1. Add all these together and divide by however many of those you had. But if you let that go down, basically what you're doing is I haven't defined this too well. I really find it a little sloppy here. Oh, they're using right endpoints. That's what they're doing. Okay. That's what the capital R stands for. I'm going to blow this up a little bit just so it's a little easier to see. Ignore my chicken scratch above there. Okay. So the average values of this function f at these points, and notice they're using x of 1, x of 2, x of 3, up to x of n. You could have used x of 0, 1, 2, 3, and just gone up to x of n minus 1. The right, you're using the right one, the left, you're using the left one. Okay. So the average value there would be, what they say, that capital R sub n, they say that's the right hand, let's see, get this again, is, they're taking you back to, I don't know where they're taking you back to, they don't say. They say recall the formula for right endpoint approximation, which goes back something much earlier, and they give you the formula. But let me give you a better clue on this. Picture the area under here, right? Okay? The area under here. Let's say we knew what that was. Divide that by the length, b minus a, and that gives you the average. So rather than saying, go back to right-hand formulas, which are, stuff like this, picture this as being the area under that curve. Divide it by the length, that's going to give you the average. That's where they're heading. And why take you back to Riemann sums and formulas I don't commit to memory or anywhere else, use it, but this is what you get. So here is your average value. Okay? Now let's see if it's indeed what we come up with. All right? The average value of an integrable function. What in the world is an integrable function?
Function that
Can be integrated, so therefore needs to be continuous. Okay? And have, I think it also has to have first derivatives that need to be continuous, so you don't have any points and things like this. So it's an integrable function, f, on some interval from a to b is the quantity. This is that length, a to b. If you do the volume of that function, which is the integral from a to b of f of x dx, that's taking that whole function there times this, that's the area under it divided by the length. That gives you average value. To me, that makes a lot more sense than trying to tie in the Riemann sums and going through formulas. That's what you got. Okay? Now, the average value is also sometimes called the mean value. So when my wife says I'm mean, I say, no, I'm way below average. Okay, no problem. Okay, that's called the mean value. And then they say the same thing too, and here's the figure they're going to use for that. This is what I was just telling you to do, okay? In a sense, you might not recognize that's what I was saying, but indeed it is. If you were saying what is the mean value of the first lobe of the sine function from 0 to pi, what's the mean value there? Well, we do the area under this and divide it by the length, okay? Well, how does that give you mean value? Well, picture you take this area and you force it into a rectangle, same area in the tan here is in the gray here. Force it in there, this would be, the length is the same, this would then be the average value. And that's exactly what you get. The area under the graph is equal to the area of the rectangle whose height is the average value L. So that's where that came from. Now they happen to, in so doing, just give you the answer for example 7, so I shouldn't have done that yet. So let's do example 7, which is this. Find the average value of f of x equal to sine x on the interval from 0 to pi. Can anyone tell me what it be 0 to 2 pi? Graph of the sine function 0 to 2 pi. You have the same thing above as it'd be 0. It'd be, so that's why it is 0 to pi. Okay, gonna give you a little bit more meaningful answer maybe. So how would we do this? The average value would be 1 over pi. B minus A, pi minus 0, times the integral from 0 to pi of sine x dx. Okay? This is 1 over pi, antiderivative of sine x, negative cosine x. Yeah. Evaluate it from? Okay. Okay. So this will be 1 over pi. Now, watch these minus signs now. You have a minus. Okay. What is cosine of pi?
That's 0.
No. No. Cosine of pi is, it starts at 1, yet it goes to negative 1. So that's minus a minus 1, minus a minus, which is a plus, and cosine of 0 is 1. Okay. So this will be 1 over pi times So there'll be 2 over pi. So that's approximately 2/3. Not quite, but pretty close to it. So let's go back to this one. And if this is 1, that looks to be about 2/3. Yeah, close. Of course, it's a little less than 2/3 because pi is a little bit greater than 3. 3.141516. So yeah, that would be a little bit less than 2/3, but it's awfully close. And that sure enough does look like the average value, 2 over pi. And they do give you 0.637, whereas 2/3 would be 0.667. Okay. So off by 100. All right. Let's do it here. Vertical jump of a bush baby. The bush baby. And by the way, when you see that genus or the biological name for it, when it starts with Gallico, I think Galapagos Island. I don't know that that's where it's from, but I wouldn't be surprised. Okay, because they have,
Galago.
Yeah, I don't know if that comes from Galapagos. You know where the Galapagos Islands are?
Galapagos, yeah.
What they're famous for?
The tortoises.
What's that?
The tortoises, the big turtles.
Oh, they do have huge. They have some of the most unusual animals on the planet.
Right, and that's also where Charles Darwin.
He went, and that's where he sort of developed a lot of his evolutionary theory, because they developed differently from animals elsewhere, maybe because they didn't have the natural enemies or other things else. They're islands off the coast of South America, not too far from Ecuador. Go off the coast, you have to fly or take a fairly long boat ride. Very separated, and the development of the species there, huge turtles, bush babies, seems like maybe some platypuses are very different there. There's just a lot of very interesting wildlife, not just animal, but I think plant life too.
I think their tortoises even live longer, if I'm not mistaken. They're not just bigger, but actually their lifespan. Normal tortoises, their lives are really long anyway.
Right.
Theirs is actually extended even more, so it's crazy.
Yeah, I just assume it's for lack of natural predators. Yeah. And so they just got used to it. Okay. But here, the vertical jump of a bush baby, okay, and by the way, the bush baby is a small primate. There's a picture of him. Oh, we'll blow it up so you can see him better. Okay. I'm blowing up a bush baby. Oh no. It's the bill. Okay. Okay. With remarkable jumping ability, find the average speed during a jump if the initial vertical velocity is v0 is equal to 600 centimeters per second. Okay? And we use Galileo's formula for the height, h of t. So we're going to have a couple of things here. So I got to get out of here to do this. So his v0 is going to be 600 centimeters per second, which is a pretty fast. That's 6 meters per second. That's moving. Okay.
It's funny how your book mentions Michael Jordan as the.
And the new book mentions Blake Griffin.
Yeah.
And I went, who is Blake Griffin? I mean,
Right.
In between there may have been additions with Kobe Bryant. No, who was the big jumpers? He wasn't that big a jumper, that's right. He was a scorer, but not a jumper. But anyway, yeah. That's right. This is Michael Jordan, the book says.
I just
Blake
think that's
Griffin.
funny that they even compared that. I mean, Blake Griffin's great, but it's not Michael Jordan.
I don't even know who Blake Griffin plays for. It shows how ignorant I am. LA Clippers. Okay. Okay, find the average speed during the jump if the initial speed, V0, is 600 centimeters per second. Use Galileo's formula for height, which is h of t is equal to V0t minus 1/2 gt squared. Okay, now we won't go through and get this. If you've taken physics, you've been there, done it. If not, you're going to take it, you'll get there. We'll just leave it alone for now. Okay, now, since we're dealing with centimeters per second, this g that we use here, we have to have, normally we say g is 9.8 meters per second squared. That's going to be 980 centimeters per second squared, because you got to get in the same units everything else is. Okay. Now, the average speed during the jump, if the initial vertical velocity is that. Okay. Now, they do some sort of strange things here, I think. I just wouldn't quite do it the same way they do. All right. Okay. The first thing they're going to do here, which is a pretty legitimate way to approach the problem, is that I really don't see a huge reason to. Yeah, I know why they're going to do it. So they're going to take this height, and the first thing they do, which is, I think, a little bizarre, factor out the t. And that'll be t times v0 minus 1/2 gt. Okay? Now, there's a reason why they did that. Okay? It may not be exactly obvious, but there is. The height is 0 at t is equal to 0. That's when he first jumps. And then again, when he reaches the ground again, after the jump, and that's going to give the time that he was in the air, right? So when he comes back down, that's going to be v0 minus 1/2 gt is equal to 0. Okay? That's when he comes back down. What time would that be? V0 is equal to 1/2 gt, and then multiply by 2 and divide by g. So that's going to give you the time when he comes back down. Okay? So this is how long he was in the air. Okay? 2v0 over g. Now, if you want to plug in what that is, it's 1200 divided by 980. Okay. Perfectly fine for you to do that if you want. Okay.
1.22.
That sounds reasonable. Okay. That's the time that he reaches the ground, 1.22. Yeah, whatever. Okay. They just leave it, for some strange reason, 6 over 4.9. Okay. Well, not 60 over 49. I don't know how. Okay. That's when the jump ends. The Bush baby's velocity is h prime. So another thing you got to do is take a derivative. H prime of t is equal to, and taking the derivative of that, that'd be v0 minus minus gt, right? Plus 2 cancels that one out. Okay. Now, plugging in what those are, that would be 600 minus 980 t. Okay? Now that's the change of That's the speed at any time t. Okay? And certainly at when you set that equals 0, that's going to be when he's at the top, right? When he's at the top. When would that be? That would be 600 over 980, which will be, that's going to be t at the top, the time that he reaches the top. That's what, okay. And that would be, should be exactly it's exactly half of what that is, right? That's 2v0 over t. I don't quite see, you said 2.2, didn't you? I think it was more like, one, okay, yeah, okay, good. I was going to say that. Can't be that, okay. Yeah. So that's exactly half. Now, I don't think they did this in the book, and I don't see why not, okay? But anyway. The velocity is negative anytime past that, okay? And the integral of the speed is equal to the sum of the areas of the two triangles, okay? And they show this figure here, okay? Because the speed here, initial speed is 600, it falls off to 0 when he's at the peak, and then it's negative from then on, but it's saying add these two together. Okay. My question is why? Because the average speed going here, average speed going here, why don't you just take that part right there and do it from that? I see no reason to have to fiddle with the trip down. Is average speed going up is the same as average speed coming down. If you ignore wind resistance, which we have all the way along, so why go through all that? Just take it right there, and that would give it to you. Let's see what we get. And I mean, they can really make it sort of complicated. They do the integral from 0 to 6 over 4.9. Again, they don't give a number there. They just use that. And then they do absolute value, which you do two different pieces. But why don't you do, just do this instead of what they did. Do it and see if you don't get the same answer. S bar is equal to 1 over 3 over 4.9. Okay, that's, let me make sure I got, yeah. They just did everything divided by some weird number. Okay, so 3 over 4.9 times the integral from that, but don't do absolute value, just leave it 0 to 3 over 4.9. Why they do that, I don't know, but they do. And then just do 600 minus I think that's all. 600 minus 980t. I think that'll do it. dt. I'm using their approach. Yeah, 600 minus 980 dt. Okay. So it'll be 1 over 3. Why do they do this? Let's just make this 4.9 over 3. That's the same thing. Okay. And this integral will be 600t minus 490t squared, right? Right. Where did it go? There it goes. Okay. Evaluate it from 0 to 3 over 4 point. I just don't know why they hang around with numbers like that, but they do. Okay. If you'll plug that, well, you've got to figure out what 3 over 4.9 is. At some point, just don't undo it. It looks like to be about 0.6 or so. A little more than 0.6, right? 3 divided by 4.9.
0.6122.
Okay, whatever that, 0.6122. Okay, so 600 times that minus 490 times, okay, minus 490 times that same 0.622 or whatever you said it was, 6122 or whatever it was, squared. Okay. In other words, you know, what did you say this was? 0.6122?
Yes.
Okay.
And 3 over 4.9.
Well, yeah, but do 4.9 over 3.
Yeah.
Multiply by that, yeah. Yeah, oh yeah, 3 over 4.9, that gives you that number. Plug it in here.
That's why I was saying times 600 is 367.347. I didn't know if you just want it right now. I was plugging it in.
Okay,
right
how
there
far
at
along?
Right there at the 600.
Yeah.
I was plugging in for T.
Okay, 600 times that
Yes.
minus 490 times that squared. Okay, I did the zero part. Okay, then multiply that by 4.9, divide by 3. And I sure hope you get about the same thing they do. Okay, has anyone got an answer yet? Now, they kept the fraction form there, which probably got a more precise answer, but we still should get close.
Is it 183.6?
Well, that's not what they got, so maybe my method isn't right, but they got 300 centimeters per second. Huh?
I got 300.04.
Yeah, that's it. Okay.
Yeah.
So why carry it this over here? If this is a total of that, just do from here to here, which is your 3.
Yep.
3, okay. Why in the world they use such weird numbers? They do 6 over 9.8, or you did 3 over 4.9 if you're going this. So yeah. So just do half of it. Now they did a lot of extra work, and I couldn't really see a reason why. Took way too much time on that problem, but it is pretty interesting. Average speed of 300 centimeters per second. 3 meters per second. Wow. Okay. Really fast. Which, when you get down to it, is exactly half of this, because that's all linear. Half of 600 is 300. Yeah. We could have just gone right there. Because half of the area under there is this triangle, this rectangle. Yeah, that's what you should get as an answer. Okay. Now, here's that same, or it looks like the same figure we just did, except this doesn't call it a sine function. Though it looks identical to what we did before with a sine function, so I don't really know why they reproduced it twice. But the function f of x takes on its average value m at the points where the upper edge of the rectangle intersects the graph. Okay. For any function that does a smooth shape like this, that's going to have 2 values there. Okay. If it did a lot of wiggling and jiggling, it could have many more than 2. If it was a function like the triangle or something we did, then it's only going to have 1, but it's always going to have at least one place where the function has exactly its average value, at least one. Okay? Which leads us to the mean value for integrals. If f of x is a continuous function on a to b, no gaps, no holes, nothing like that, okay, then there exists at least one value c on a to b such that f of c is exactly equal to that mean value. So if it's a triangular thing like we just did, it's just going straight down here. There's one value that's exactly that. If it's a parabolic or sinusoidal or something like that, then there will be two. But there's at least one place, C, where it takes on that mean value. Alpha C is exactly that. Now, remember the mean value theorem before for functions in general. If you have a continuous function, the f of a is not equal to f of b, then there's at least one place in between that where your function takes on any value between that. That's intermediate value theorem. Okay. Now they do a little proof with that, but the book doesn't. I mean, the slideshow doesn't go into it. So that finishes 6.2. Boy, we beat that to death, didn't we? Do y'all find the preliminary questions are useful to go through those? We've been doing them, but I don't want to do them unless you feel like they're beneficial to you. Yay or nay? Okay, let's do it. What is the average value? Whoa. Let's see. No, we've got another hour. Okay. What is the average value of f on 0 to 4 if the area, let me go back. Yeah, we'll do this. What is the average value on f on 0 to 4? So we're looking for average value of f on 0 to 4 if the area between the graph of f and the x-axis is equal to 12. If the area between the graph of f and the x-axis is 12. Yeah, okay, is equal to 12. So what's the average value of that function? Three, exactly. Because what they're saying there, the area is this thing right here. That area is 12, and the average value would then be 1 over the difference, 12 divided by the difference between 4 and 0, so that's 12 divided by 4. Perfect. Well, that's the wrong formula, but yeah. I mean, the right formula, but use a different context. Very good. Okay, number 2. Find the volume of a solid extending from y is equal to 2 to y is equal to 5 if every cross-section has the area A of y is equal to 5. Okay, so let's just say we have, trying to think how to draw this three-dimensionally without getting too wacko here. Let's make this the y-axis, okay? And the y is going from 2 to, why am I losing it? Yeah, 2 to 5. And every volume here this area all along here, every one of these areas, the area is equal to, keep losing it, 5. Okay, whatever square units that is. A of y is equal to 5. Every one of those is 5. So what's the volume of that shape? By the way, if all these areas are the same, we assume it's a uniform whatever, okay? Area of every cross-section area there is 5. Every one of them is 5. Okay? Yeah. From 2 to 5. Yeah, the length from that is 3.
Times the sum, right?
Yeah.
Okay, times cross-sectional area
Is 5.
5. Yeah. Oh, the area is 5. Okay. So
Yeah.
Times 5. Then.
Yeah.
So
3 times 5 is 15. Yeah. That would be 15. By the way, we ought to probably check and make sure they're getting the same answers we are, but I'll see how they could be otherwise. 3 and 15. They got those two right. Good for them. All right. What is the definition of flow rate? You can turn back in your summary. Well, it's not in the summary. Just turn back and find the definition for flow rate. Okay? I'll let you do that on your own. Which assumption about fluid velocity did we use to compute the flow rate as an integral? Which assumption about fluid velocity did we use to compute the flow rate as an integral? Laminar flow, you got it. Yeah. And that means that you don't have any turbulence in it. Turbulence screws everything up, so laminar flow. I'm pretty sure that's what they're looking for. Well, actually, it's the same thing. The fluid velocity depended only on the radial distance from the center of the tube, which I think is the definition of laminar flow. But let me just see. Well, I don't see it now. But yeah, here it is. However, for a slip, which might mean that the velocity depends only on the, yeah. They just gave you the definition of laminar flow. Okay, number 5. The average value of F, okay, they started with this, not quite the same. The average value of F on 1 to 4, okay, not quite the same, is 5. Okay, new problem here. Average value lost it again, of F on this time 1 to 4 is 5. Find the integral from 1 to 4 of f of x dx. Remember, average value is equal to 1 over b minus a here, which is 4 minus 1, I'm sorry. They told you this is 5, so what is that? Second? No, you multiply. Isn't that? I think that's right. Yep. See, this average value is 5. That's 1 over 3 times this. Multiply both sides by 3, and you get this. So it's 15 again. You see that? because this is 1 over 3. Average value of 5 is 1 over 3 times that integral. What's the integral? It's multiply b minus a, which is 3 times 5.
I thought we were looking for the function.
Yeah, no, not for the function. For the
Yeah,
integral.
the 15, I thought we had to find the function.
Okay, good luck with that. Okay. They didn't give you enough information for that, maybe. You could come up with a function that would give it to you, maybe. They just say, what is that? Okay, homework exercises here. I would do some of the odds 1 through 7. I'm not going to say just stop at 1, but do enough of those so you feel really comfortable with them. Then do some of the odds 9 through 13. Do some of the odds whole bunch of these, 15 through 37. Okay, and again, I wouldn't maybe just do 1 or 2. I would do some of each type, 15 through 37. Okay, then do some of the odds 39 to 47. Those are all pretty much the same. I'm sure with different levels of complexity, but then do some of the odds 49 through 65. Some of those you may or may not be, or won't even want to do. 65, for instance, is sketching a graph, which is sort of a fun exercise. There's not really a lot of calculations in it, but do some of those too. Any questions on those? 6.2. All right. If not, let's move to 6.3. Sorry, PowerPoint has been taking a long time today. Hey, actually it's moving faster now than it was earlier. Boy, this morning just sat and watched it, like watching paint dry. All right. Volumes of revolution. I'm trying to start a revolution here. A solid of revolution is a solid obtained by rotating a region in a plane about some axis, and they give a couple of examples here. I don't know if blowing this up will make it any clearer. Let's try it. Let's do these first. All right. If you have this plain little old triangle here in the XY plane, but revolve that around the y-axis, then you get a right circular cone. Because everything here is revolved around, so that gives you a circular base, and every smaller radius gives you circular bases until you get up to the point. Right circular cone. Okay? Now, just why are they saying this? What we're going to be doing is calculating the volume of that based on what this is. Okay? We'll be doing them a couple or more different ways. Now, if we take, like that better, if we take a semicircle, sure, it's pretty easy to find out what the area of this is. But how do they extend that to give you the volume of the sphere? Okay? Because when you rotate that around the x-axis, you get a sphere. Okay? Now, both of those they showed were functions. You could take this semicircle and rotate it around there, but then you have to do something with y because it's not a function of x. So you could do it that way too, but this way is doing the giving you with a constant function of x rotated around the x-axis. Okay. That's sort of leading in to what this section is going to be about. And here we have a a weird seeming function, or at least seems so to me. Whatever this shape is, here's your f of x. That doesn't have to be something as simple as a straight line or a circle or something. Any old function f there. Now let's rotate that around the x-axis. And what do you get? It looks to me like an old Christmas stand. You know, the bottom there's the top of the Christmas tree stand. How do you approximate the volume of that? Well, since we're given dimensions on x, it's going from a to b on x, looks like to me dx would be a good choice here. Integrate from a to b along x and have a dx. Well, dx is going to be a little sliver like that, okay? Very thin strip there, okay? Now, if you can take that dx, okay, and rotate that around the x-axis, that gives you a single disk like that, or a circle, you might say, because you just extended this all the way here. This part went here, this part went there, you know, every part in between. So, what is the cross-sectional area of this? Well, that would be pi times this radius squared. Okay, what is that radius? It's your f of x, right? At this value x between a and b, the radius here is f of x. So assume you know what that is, or they give it to you, somehow know what that function is, okay? Then pi r squared, pi f of x squared is going to give you that area of that disk. That's as a function of x, and that's the volume of that would then be times the dx, okay? The area times length is volume, and then sum all those from a to b. So basically you have the integral of from a to b of pi, put the pi on the outside, pi times the integral from a to b of f squared dx. The square of that direct pi r squared. And then you do sum those or integrate those from a to b. Okay? So that's called calculating the volume of revolution by the disk method. Okay? If f is a continuous function and it's always greater than 0 on a to b, then the solid obtained by rotating that region under the graph about the x-axis is the volume within or with r equal f of x of pi r squared or pi f of x squared integral of that a to b dx. Now, this book does this, and I don't know why. I don't like this notation because just almost glancing at it, you might confuse that to be f of x squared. No, it's not. I like to put the square here to remove all doubt. Okay, f squared of x. I would write it that way, but this book writes it f of x squared. Especially saying that, you don't know exactly what you mean. Looking at it, you have a pretty good idea. If you say f squared of x, it's obvious. Now, the phrase I just said reminded me of a quote. I think it's from either Mark Twain or Will Rogers or somebody. It said, and it has nothing to do with this, he said, it's better to be quiet and be thought a fool than to open your mouth and remove all doubt. So that has nothing to do with what we're doing here. But anyway, I just like that phrase, that quote too. So that's how we do a volume of revolution, the disk method, when we're revolving around the axis that we know the function is the function of that axis. It's a pretty simple process, in theory anyway. Okay? So let's do example 1. Okay, I think this is the same. Calculate the volume V of the solid obtained by rotating the region under y is equal to x squared. Yep, that's what we've got down here. I'll blow it up now for you to see. Okay, y is equal to x squared. That's that parabola. Now, I guarantee you what they've done here is expand the x-axis and kind of shrunk the y-axis here. Most parabolas go up faster than that in my book, so they've done some scrunching here on the thing. Because this value right here should be 4, and this value here is about 1 on this scale. So they have done some compressing or expansion. But anyway, there's your graph. Okay. Calculate the volume V of the solid obtained by rotating the region under y is equal to x squared. This right here. Okay. About the axis from 0 to 2. Okay. So you got a megaphone. Okay. Type looking thing. Okay. Let's get rid of that. How would you find that? What is that volume? Let me get my pen done. V would be equal to what? Okay, let's go down here. Y is f of x. There's your f of x. Okay. What's the formula for the volume? Yeah, that just is. Yeah. Oh, you want me to go back? Oh, I see. Okay. Yeah. Oh, I see. I'm sorry. I didn't give you time to write. I was sorry. You should have made me stop earlier. Okay. Make it a little easier to read here. So, what's that volume? Pi integral from some what? 0 to 2. 0 to 2. No, not of x squared. It was your f squared of x. Your f of x was x squared. F squared of x, which is what you use there, because it's pi times that radius. This radius, see, here's your x, there's your f of x, and you're going to square that. Pi times that radius squared. Okay, so that's going to be f squared of x would be x to the 4th. Very good. So it'd be x to the 4th, then dx. Okay. Now again, I like to picture this. Okay, here is the, if you go out x here, it's the integral, okay, the pi r squared is this, the function here, the y value here, which y is x squared, pi times that radius squared, that's why that comes with x to the 4th, times dx, integrated from 0 to 2. So pi times this thing squared, dx integrated from 0 to 2. And what does that integral produce? Say again? X fifth over 5. And that would be evaluated from 0 to 2. That would be pi times 32 fifths. Okay, that's it. 32 pi fifths. Or something like that. How do they write theirs? 32 fifths pi. Okay. Again, I don't care which form you do it. Okay. That's called the disk method. That's specifically if, again, when you do your thing and you rotate your stuff, what are you taking the increments of? You're taking increments dx, and this is defined in x, and then this works like a chart. Okay? Now, What if you weren't just interested in the x-axis, okay, being your region? You got some other complication here. For instance, when you do it, to me, they do this kind of backwards. They give you this first, and you sort of say to yourself, why are they giving me this? Okay, what's the purpose of this? But it's just an observation here. What if this is indeed what you had, not a disc, but a washer, okay? It's not something that washes clothes with, a washer. And the region between two concentric circles is called an annulus, by the way, or more informally, a washer. And the area between those would then be pi times the outer radius. That would give you the area of the whole thing here, minus the area of the middle thing. So just imagine all this was pink, then you cut out the pink part here, subtract that, that gives you the area here. So it's pi, again, because you have pi in both of those, times r outer squared minus r inner squared. Okay? That would be the area of a washer. So why do we need the area of a washer? Well, what if we had a situation, I want a picture first. Here. So what if we were going to take this region, okay, with me. Can I get it all on here? No! Okay, I'll get what I can on here. Okay. So what if we're taking that area and rotating it about the x-axis? Okay? Well, obviously, you're not going to have the same solid of rotation because you got a hole in the middle here. And that then forms the washer that we're talking about. Okay? So here it's bounded by some function f of x up here and some function g of x up here. That whole thing you're rotating around the x-axis. So then you'll have pi times this squared minus that squared. Pi this squared minus pi this squared. The outer minus the inner, that gives you that whole area. That would be the area of this disk of thickness dx. Okay? The outer minus the inner. So that generates the washer that we were talking about before, and you add all those up, and this really does look like a Christmas tree stand now, doesn't it? There's a hole that the tree goes into. Okay. Sometimes that's called a frustrum too, except, well, there's a little bulge in here, but you don't see it except in the picture because it's had a curve to it too. That doesn't matter. Anyway, that's the volume that you generated there. Okay? So let's go back and see that formula, and here it is. So the volume by the annulus or washer method, if you have an inner and an outer, then that would be v is equal to pi. That pi is always out there. Integral from a to b, that's the length along your x there that you're doing. The r outer radius, which is typically your f squared, and I like to put the square up there, minus r inner squared, which is your g squared of x, times dx. So this is in terms of the r outers and inners, that's in terms of alpha g. But remember, you can do it however you want to, but I'll always write that f squared of x minus g squared of x. I don't like putting the square after the x, just because there is a really outside chance you might misinterpret. F squared, to me, that's pretty obvious. All right, let's do example 2. Is this example 2? I think so. Okay. So, example 2, find the volume V obtained by revolving the region between y is equal to x squared plus 4. There it is. Okay. And y is equal to 2. There it is. Okay. This is really looking more like a Christmas tree stand now, because that's a straight place for the truck to go down. Okay. Sorry. Revolving that around the x-axis. You're doing it between x equal 1 and x equal 3. Okay? Now, maybe in the verbiage here, but I don't recall seeing it. But notice a couple things here I'm not sure they said yet, but they should have. Maybe they did. This F up here has always got to be greater than or equal to your G. Got to be. Otherwise you get that would be a mess. Okay? And so far, and that's always, got to be greater than G, but it's also greater than or equal to G, but it's also got to be greater than or equal to 0, because G's got to be greater than or equal to 0 for you to revolve it around and get a hole in the middle, so some sort of hole. So you've got to have both of those. Okay. So anyway, that said, let's do the math. What's the region between those two curves? Volume is pi. Always got that, because you're revolving something around basically a circle. The integral between 1 and 3, that guarantees you got a dx here, because that's along the x-axis. So you got to have the dx. Okay, what next? Okay, x squared plus 4 squared minus 2 squared, which I'm just going to write as 4. Is that okay? And then your dx. Now let's see what that gives you. Pi times the outer radius squared times dx minus pi times the inner radius squared dx. Yeah, that gives you your area, and the dx gives you your incremental length. Area times length would be volume, and you integrate that over the entire range of 1 to 3. Okay? What would you do first? Say again? I can't hear. What would you say? Oh, I wouldn't, I don't think. I would square. You got a function, you got a square there. Yeah, let's square it. What would that give you? A little louder. X to the 4th plus 8x squared, good, twice the product of the 2, plus 16 minus 4 dx. Goodness. We can do just a little bit of simplification by combining like terms. 16 minus 4 is 12. Okay. I didn't think that was worth writing down, so I just scratched through it. Now I think it's time to integrate. And what do you get there? Pi. Say again. X fifth over 5. 8x cubed over 3, 12x isn't it 12? I'm sorry, 1. Goodness gracious, where's my brain? Wait. I went to hit an erase and I hit the wrong thing. 12x, sorry about that. Okay. and you evaluate that from 1 to 3. This doesn't have a 0 in it, so you're going to have to do them both, okay? Get the pi out there. I like the sound of that. Anyone happen to know what 3 to the 5th power is? 3 squared is 9. 3 to the 3rd is 81. Say again? 243. 243 fifths plus
72.
say again?
72.
76 thirds? Huh?
72.
73?
2.
2. I can't hear. 72 thirds?
No, sorry, it's just-
Oh, okay, you already did that. I was going to say that number doesn't sound big enough, but yeah, you had already done that. So, yeah, let me. 72. Okay. Plus 36. Minus 1/5. 8 thirds. Minus 12. Okay. I'm not sure writing it this way will help a lot. It helped ever so slightly on the first one, but not much. 242 fifths plus okay. Goodness.
108.
Okay, yeah, sorry. My head's just sort of going wonkers on me. I feel like I might have a migraine coming on, but I hope not. Okay. So what are you doing now? Getting that in terms of fifths or what? Let's not do it yet. What you added those two together. Good idea. Well, how about let's adding 72 and 24. Subtracting that. Okay. So that would be 96. Okay. And then we've got a minus 8 thirds. Okay. Boy, the calculus is the easy part. It's these stinking fractions stink, right? Okay, never mind. We didn't say that, did we? Okay. If you're doing it the right way, let's at least get these two numbers into 15ths. Okay? So that would be 7/26 15ths. Did I do that one right? First one, multiply the top by 3. Okay, minus 40 15ths. Is that right? Okay. So that would give us 686. 15ths would be that part, and that is a plus to 96 now. I don't know if I want to write that as a mixed number. Probably not. So I guess we're going to have to get 96 to 15. So 96 times 15 is 1,400 what? 40 15ths plus that. That would be 2,126. I can't read my writing. 15ths. I think we'll just leave it like that. Yes. Oh, and I forgot my pi. The pi's in front of all that, or behind it in this case. Okay. 21/26 15ths pi. What a nice round number. Okay. To have as a volume. Okay. Does that make sense? Okay. Let's move to example 3. Now this is a fairly interesting kind of shape here. Let's blow it up to begin with. Take a look at it. Can we get it all in? Oh no, Mr. Bill. No, not quite. So let's at least get this part in. Okay. So what we have here, find the volume V of the wetting band, figure 7C that we have here. Yeah, this is also 7C, except you can't see C yet. Okay. Obtained by rotating the region between the graphs of f of x equal x squared plus 2 and g of x, which is 4 minus x squared, about the horizontal line y is equal to negative 3. Whoops. They don't use the x-axis on this one. Y is equal to negative 3. That's what you're rotating around. Okay? You really do it the same way, but you're going to have to do perhaps just a tad more thinking about it. Now, number one, they just said by rotating the region between the graphs. Now, they drew the graph for you. Most of the time on a test, I'm not. I'll promise you, I don't usually like drawing graphs. So you're going to have to figure out. So if that's all that was given, then you got to figure out, number one, who's on top, and number two, what the points of intersection are. So let's do with the intersection first. How do you determine that? I'm going to have to reduce it to do this. What do you say? Set them equal? Yeah. 4 minus x squared is equal to x squared plus 2. Probably should have written it the other way, but it doesn't matter. And what would you do to set those equal? Add x squared to both sides. And then, let's go get your x squared over there. I would say subtract 2 from this side. Okay? All right. This will be 2 is equal to 2x squared. Right? So x squared is equal to 1. So x is equal to plus or minus 1. All right, that's doable, and that's what they got in the book, or at least it looks that way. Okay? So we know we're going from minus 1 to 1. Unless, of course, you notice the symmetry there, and you decide, let's just go from 0 to 1 and double it. That will be fine. I like being lazy most of the time. Okay? So, we got that part done, or at least thought through. Okay? What's going to be our integrand, though? Okay. How does it typically go? Pi. All right, I wanted that part. The volume of this, I think that's what they're asking for, right? Find the volume out, okay? Pi, the integral, and we're going to do 2 pi because we're going to double that. We're going to go from 0 to 1, okay? Y'all are all in favor of that? Okay. Now, what was the next part? Outer radius squared. But what is the radius here? It's not this function here squared, because it's this function here, that's the outer one, the one up here. They drew it for you, but you see, this is concave down, this is concave up. It's almost got to be this way, okay? So it's this distance here from your point of thing. So it's 4 minus x squared minus a minus 3, which would be a plus 3. That's the radius you're dealing with. And that's what you've got to do here. So I wish I could keep it blown up and write on it. I can't. So that would be 4 minus x squared minus a minus 3. That's the length of that outer radius. Okay? Which when you do that, that's 4 minus x squared plus 3, which would be 7 minus x squared. Okay, and they do a G plus 3, which is fine. That gets you the same thing. Okay, so that's going to be the first one. 7 minus x squared squared, right? Minus x squared plus 2 minus a negative 3. So let's just going to make that plus 3. So that's going to be x squared plus 5 squared minus x squared plus 5 squared. Then you got your dx, because that's the thickness of every one of those little bands, and you got it. At least you've made progress to getting it knocked. You still got some work to do. 2 pi. Let's keep the integral here for now. Let's square that first one. What do you get there? Anyone square that first one? 49 minus 14 x squared plus x to the 4th minus, now you want to keep it in parentheses, or can you change all the signs as we go? Huh? Keep it in parentheses for now. Okay, let's square that one. What do you get? X to the 4th plus 10x squared, right? Plus 25. Inside there is plus 25. And that will be times our dx. Okay? Let's come down here. 2 pi times the integral from 0 to 1. Now can you do the subtraction, or you want to write it out? Yes, the x to the 4th go away. That's the good news. Second? Okay, 49 minus 25. Let's go on and do that one. That would be 24, won't it? Okay, and then you have a minus 14 x squared minus 10x squared, so that's a minus 24 x squared dx. Now, before I start, I hope I did that right, didn't I? Okay. Before I start doing it with any integration, I think I want to pull out a 24, don't you? Why not keep life as up? So if you factor out a 24, that becomes a 48 pi integral from 0 to 1 of 1 minus x squared dx. I think we can probably do that. 48 pi times x minus x squared over x cubed over 3, right? Okay, x cubed over 3. Whoops. Evaluate from 0 to 1. Hey, this isn't too bad, is it? That's a 48 pi. And what does that end tide give you? 2/3. That's all, folks. 2/3. So I can do the 3 and the 48. That goes 16. That's 32 pi. I sure hope that's the answer. Yes, it is. Look at that. Now, they did minus 1 to 1. Fine, you can do it. But why do all the extra math if you can avoid it? Okay? All right. Any questions on that? I'll leave it up there a while if you need it. I'm sort of right all over the board, so if you don't mind. Go back and watch it on YouTube, and you'll see which one comes first if you get lost just looking at this. Make sense? Any questions? If you have them, good time to ask. Everybody okay with it? If you have a question, ask. Did you? Huh? Good? Okay. All right. All right, let's go to, I think it's example 4. I believe this is it. Okay, let's blow it up and see what we got first. Can't get it all on there, so let's split it out about like this. Okay. Find the volume obtained by rotating the graphs of f of x equal 9 minus x squared and y is equal to 12 for 0 less than or equal to x less than or equal to 3 about the line y is equal to 12. Okay? Now that's going to be the first part. Forget about this 15 for now. It's this graph, f of x is 9 minus x squared. Now again, if I were giving you this on the test, all you have is the words, you don't have the picture to go by. So you basically have to draw your graphs and see who's on top. You know, to know which one gets divided or multiplied or squared or whatever first. Okay. So here is your function, 9 minus x squared. Now this has really expanded the x-axis big time because that looks like that's about 1.5 this way and that's about 10 that way. So yeah, this isn't, the x and y axis aren't using the same scales, but the picture's okay. Maybe it makes it easier to see. So 9 minus x squared, you know that's going to be a parabola concave down with the vertex at 9. Okay, you know that. And this one up here at 12, so yeah, y is equal to 12, that's up there. Okay? Now, but you're going to rotate this not about the x-axis, not about something down here, but about that upper line here. So now, your outer radius is this one, and your inner radius is here, except in this case, there's no inner radius. That's the line you're rotating around. So basically, your radius, this is going to be a disk method because you don't have any separation here between your axis of rotation and the top line. It's the same. So this is just going to be this length, pi r, well this is the r, that length squared times this. Okay. But it's this minus that is the length. 12 minus this. Okay? Does that make sense? Okay. But guess what? If you subtracted the other way, you're squaring it anyway, you still don't get the same answer. But let's sort of do it right. Okay? So that will be actually a disk method. So let's do that. Find the volume obtained by rotating this function around that line. The graph between the function and that, around that line. So what's going to be the formula for that, the A part? Say again? I think it's just pi, isn't it? At least for now. Okay? Because it's pi r squared. Okay, so let's just start with the pi. Okay, we'll do the integral. What's the integral going from? 0 to 3. Okay. Now, and this is going to be a dx because it's integrating along the x-axis, and that's where your limits are. Okay, everything's on x. Now, what is the length you're dealing with? Okay, you say 9 minus x squared. Okay. I kind of like to do upper minus lower always. Okay. 12 minus this. Right? That's going to be 3 plus x squared, right? 12 minus 9 is that, and then minus that. So that's going to be a 12 plus x squared, isn't it? I mean 3 plus x squared. 3 plus x squared. That's that length squaring it. Now if you did it the other way, guess what you get? 9 minus x squared minus 12. Okay? That would be minus x squared minus 12. Minus 3. Minus x squared minus 3. Or 9 minus 12 is minus 3. And you're going to square that. And guess what? It's the same entity. It's just a negative squared. It's going to give you the same thing. Exactly the same. But you just missed the opportunity to make all those errors with the minus signs if you do it this way. Okay. You still have plenty of opportunities for error. So got to square that first. What is that going to be? Pi times the integral from 0 to 3. What will that be? 9 plus 6x squared plus x to the 4th. Okay, dx. Okay, just an integration now. What would that be? 9x. Can we just call that 2x cubed? Okay. I love that, don't you? Okay. That's going from 0 to 3. Oh, joy. Okay. That's going to be a pi. I like the sound of that. Okay. And what is that first going to be? 27 plus 54 plus, oh boy, isn't that 81 times 9? 279? Is that right? I'm doing it in my head, and my head's not doing well today. 243 over 5? Is that right? Okay. I need a moment here. Oh, 27 times that. Yeah, that makes sense. Okay. And then I can do the 0 part. Done. Okay. So that's going to be pi times. I'm real tempted on this one to do it this way. 79, no, 81, right? Yeah. 81 plus 48 3/5. Did I do that right? Yeah, I think so. Okay. That would be 129 3/5. Now I guess we got to go back and make that in the fifths, probably because that's what the answer does. But that's going to be 45 and 3 is 48. 4, 648 over 5 pi. Is that right? Yes. Good. Thank you. Okay. All right. That's what we got. But the B part says, let's now rotate the same thing, the same shade here around this line y is equal to 50. Okay. What is that going to be? How will that differ here? I think I'll just erase all this. Has everybody got this so far? Okay. So let's clear this and let's start anew. Okay? What are we going to have now? The pi's still there. Okay. Integral 0 to 3 is still there, right? Now what do we do? The outer here is between 15 there and the beat down here. So it'll be 15 minus 9, which would be 6, right? Plus x squared. Squared. Right? Everybody see that? Okay. Minus, and the inner is just going to be what? 3. Squared is 9. So this isn't quite as bad as maybe you were afraid it was going to be. dx. Okay? So next order of business is the square of the square. So 36 plus 12x squared plus x to the 4th minus 9 dx. Okay? 36 minus 9 is 27. So this will be pi of the integral from 0 to 3 of 27 plus 12x squared plus x to the 4th dx. So it will be pi times what? 27x 4x cubed. I can't hear well, sorry. X to the 5th over 5. Evaluated from 0 to 3. Still thinking 5th in there, but we'll handle that. Pi times, everybody knows what 27 times 3 is, right? 81. Okay. Plus 4 times 27, that's twice 54, which would be 108. Is that right? Got it? Okay. Plus, and I believe that was 243. Is that what we had before? 243 fifths. I did the 0. Okay, so you don't have to worry about that. Okay. Now let's add those two together. I don't know if this is going to be worthwhile or not. That's 189 plus, what did we come that for? That was 48 3/5. I believe it was, wasn't it? So this is pi times 237 3/5. I would really like to leave it like that, but I know they do it this way. That's 35 3 is 38. 15 3 is 18. 11 over 5 pi. Is that what they got? I believe so. 1188 fifths pi. And unfortunately, we've run out of time before you could do the last one. So we will pick up next time, which will be next Monday, on example 5 and finish this section. Meanwhile, homework exercises in this section will be 1 or 3, or both if you choose. Any of the odds 5 through 11, do 13, do any of the odds 15 to 19, I don't think we've done any around the y-axis yet. We're going to do that next, so let's stop right there, and we'll pick up the rest of those next time. Okay? Good deal. Yes. Okay. That's right here. How do we get that? Okay. Okay, you're doing this radius now. 15 minus this function here, right? So 15 minus 9 is your 6, and minus a minus x squared negative plus x squared. And then you square that. All right, so have a good weekend. That's an order. That's part of your homework assignment. And doing math is going to make it good. Okay, all right. So do the calculus. And we'll see you Monday. Yes. I'm going to try to take care of it tomorrow. Yeah, sorry. I hope it hasn't held you up too bad. Has it? Okay, sorry. Oh, yeah. Okay, where did we start? 6.2? Oh, yeah,
6.2,
you can do
yeah.
6.3 here. It's this, and it basically just goes to this page.
Oh, just that page?
Yeah. Because next
Okay.
page goes to
That's
Y.
all the y-axis stuff,
Right.
yeah.
Yeah. And then this is 6.2.
So,
Oh, no. Yeah. I don't even remember making it. Yeah, I did.
okay.
Yeah. Any of those. I don't look familiar though.
That,
Did I do
the
them?
topographical map definitely doesn't.
And I hope I made those assignments. Okay. All
I
right.
was just going to ask if the homework that you tell us about,
Right.
is it due at one point or?
No.
or
Okay.
it's just for my
You do it for practice
Yes.
because your tests don't look a lot like this. If you have trouble doing it, then either bring it to class, and I can work any of those in class, or bring it during office hours. But remember, all my office hours are Tuesday, Thursday. I don't have beans of office hours on Monday, Wednesday. So bring it during then, and we'll work through it together.
Okay.
That's the only time I need to see your homework is if you're having problems with it. Yeah.
Okay.